Good day, great minds. Happy new week. Welcome to this wonderful session. And always remember that you are smart, talented, and a gifted child. Do have a great learning experience. I'll be taking rotational and circular motion. Now, one thing I want you to understand is that whenever we are talking about rotational motion, it is important that we also have a reflex on translational motion. For instance, we have sleeping as an act, we have spinning as an act, and we have rolling as an act. When you sleep, you are going to go towards a straight path. The type of motion that you've undergone is what we call translational motion. But when you are spinning, the type of motion that you are going through is what we call rotational motion. Or when you are rolling, let's take for instance, we roll a ball towards a surface. It is going to be rotating in the sense that the motion is going to be in reference to its internal axis, and it is also going to be going through a straight path. The motion is also said to be what? Translational motion. So the point here is that we have what we call dynamic motion. In terms of dynamic motion, we have two different types of dynamic motion. We have the rotational dynamic motion and translational or linear dynamic motion. And today, I'll be making reference to both. Coming to rotational motion, we have different terms we should be looking at. First is what we call angular displacement. Theta. Let's say we have a circle attached to an angle, an arc attached to an angle theta, which has gone towards a surface represented with the letter S. This is the distance, and this is the radius of the arc. Okay, you are going to notice that sine theta here is equal to the opposite over what? The hypotenuse. But from calculations, we've understood that sine theta is close or equivalent to what? Theta. So in essence, theta becomes the linear distance to what? The radius. So the point here is that angular displacement is equal to linear distance to what? Radius. Next is what we call the angular velocity. The angular velocity omega. The angular velocity omega is the ratio of the angular displacement to time. So in essence, angular velocity is change in theta, change in angular displacement to change in time. Next, we look at angular acceleration. Alpha. Angular acceleration is the ratio of angular velocity to what? Change in time. With all this, I'm going to refresh your memory on translatory motion. Translatory motion is said to be the motion of a body along a straight path. I remember from the elementary level that we have three equations of motion, right? First is that V is equals to U plus AT. Second is that X is equal to UT plus 1 over 2 AT squared. And third is V squared to equal to U squared plus 2AS. Now, this is what we call what? Linear speed or tangential speed. In this case, it is the final what? Linear speed. Why this is initial speed? In a rotational motion, the final tangential speed is represented with the letter what? Omega, which is called angular velocity. So here we have omega f to be equals to omega I plus the linear acceleration is represented with what? angular acceleration, alpha t. Now this is what? Change in distance. The change in distance is represented with the letter what? Angular displacement. So we are going to have the final minus the initial to be equal to what? Omega I t plus 1/2 alpha t squared. And the same thing happens here. Omega f squared to be omega I squared plus 2 alpha s. Now this is a complete relationship or difference between the translatory motion and the rotational motion in terms of their equations. Okay, now next is what we term to be moment of inertia. Okay, the moment of inertia of a body is a property of the body due to which it possesses any change in its state of rest of uniform rotation. The moment of inertia of a body is given to be I equal to mr squared, where m is the mass of the body and r is the distance, the perpendicular what? Distance from its point or from the axis of its rotation. Okay, this is the general relationship. Don't forget that. And if this is a moment of inertia, we have different moment of inertia for different what? Bodies. For instance, the moment of inertia of a sphere is given to be 2/3 mr squared. Okay, while the moment of inertia of a thin rod from its center is given to be 1/12 ml squared. While the moment of inertia of a rod from its axis or the edge is given to be 1/3 ml squared. So different bodies, different moments of inertia. Now, knowing this, let's now look at what we call the radius of gyration. It is defined to be the perpendicular distance of a point from the axis of its rotation. And the radius of gyration is given where the radius of the gyration is the letter what? K. So if we make this the subject, this now becomes K to be equal to the square root of I by the mass of the what? Body. Okay, so remember, questions can be given here, and we are going to use the moment of inertia of the given body to relate and then be able to get its radius. Okay, next we can also remember that we have the conservation principle of the moment of inertia. Okay, like I told you guys before, whatever that exists in a translatory motion or linear motion also exists in a rotational motion. Okay, good. So in that sense, let's look at torque. Torque is the turning effect of a body that is undergoing a rotational motion. The same work that is done on a translatory motion is the same work done on what? Rotational motion. And that work done is called torque. So torque, in this case, represented with the letter this, is equals to force times distance. Okay? So, if this is the force times distance, we remember that from our moment of inertia, torque is equals to force times our distance. And if that is the case, you remember from the Newton's third law of, from Newton's second law of motion, that we are told that the rate of momentum is directly proportional to the what? To the applied force. So using that, we call that the linear what? Momentum. Coming to rotational motion, what I've just described was translatory motion. Coming to the rotational motion, we have what we call angular momentum. The angular momentum, represented with the letter L, is the product of what? The linear momentum P times R. I remember that linear momentum is mass times change in velocity. Let's assume that the body is coming from rest, the initial velocity is going to be 0. So remember that linear momentum is mass times velocity. So in that case, angular momentum becomes mvi. And if you can still remember from your elementary class that velocity is equal to the product of what? Angular velocity times the radius of the body. So if that is the case, we are going to have our L to be m, v is now omega, r times r, those giving us r squared, right? And we've known before now that m times r is what? Moment of inertia. Look at what I'm trying to show you, that L is now equal to what? Omega mr squared, and mr squared is moment of inertia. Therefore, angular momentum becomes I omega also. Alright, so knowing all these things, we are going to address some questions here. Let's start with the number one. The first question says that for increasing the angular velocity of an object by 10%, the kinetic energy has to be increased by dash. We have option A 40%, B 20%, C 10%, D 21%, and E none of the above. Now it is very, very important to understand the information that has to do with energy. You know, when a body is spinning, or a body is sleeping, or a body is rolling, they are all in motion, okay? And the type of motion is said to be kinetic energy, right? And for dynamic motion, there are two types of energy present. The first one is what we call the translatory kinetic energy. That is the same thing you call linear what? Energy. And then we have what we call the rotational kinetic energy. That is the rotatory what? Kinetic energy. And the formula for translatory kinetic energy is what you've known before now as half mv squared. While rotatory kinetic energy is 1/2 I omega squared, where this I stands for what? Moment of inertia of the given body. So in this question, we are asked for increasing the angular velocity of an object by 10%. The question is, how has by 10%, how has it been increased by? So we are talking about rotational kinetic energy, right? So using the formula, rotational kinetic energy is equal to 1/2 I omega squared, right? So what can one see here? What can you see? That the rotational kinetic energy is directly proportional to the square of the what? Angular velocity. That is to say, the kinetic energy here is proportional to what? Omega squared. Using this formula, we'll move down. That is to say, if we have K2 by K1, remember this means rotational kinetic energy, is going to be equal to omega 2 all squared over omega 1 all squared. Now pay attention. For increasing the angular velocity of an object by 10%, that is to say, if the initial angular velocity is 1, the final angular velocity was increased by 10%. Meaning it's going to be 1.1 of what? Omega 1. So in essence now, we are going to have our K2 to be equal to omega 2 all squared over omega 1 all squared times K1. Okay? And that will be giving us omega 2 is now 1.1 of omega 1 all squared over what? Omega 1 is what? Omega 1 all squared times K1. So when you multiply this out, this will cancel. 1.1 raised to power squared is going to give us 1.21 of K1. Now we convert it to percent. When you want to convert to percent, you are going to do what? Multiply by 100. So times 100%, that is going to give us 121 what? Percent. This is the total for the what? For the final angular velocity. So, and the initial was 100%. So what we have here is 21%. So it has 21% of K1 of the initial is the final angular velocity. And that goes to option D. Let's solve this second question. The ratio of rotational kinetic energy to rolling kinetic energy of a solid sphere. First, what is the moment of inertia of a solid sphere? For a solid sphere, the moment of inertia is equal to 2/3 mr squared. Good. That is to say, the rotational kinetic energy here present will be equal to what? 1/2 I omega squared, right? And that will give us 1/2. What is the moment of the inertia? 2/3 mr squared times square of the angular velocity. And what would that give us? That will simply give us 1/3 mr squared omega squared. And you've known that r squared omega squared is the same thing as what? R omega is what? Linear velocity. So this means 1/3 mv squared. Good. Next is our total kinetic energy, translatory kinetic energy. That will give us what? What you've known before now, half mv squared. So we are looking for the ratio of the rotational kinetic energy to what? To the rolling kinetic energy. And you've known before now that when you roll a body, like I've explained in the beginning of this class, when you roll a body, it is both slipping and spinning. That is to say, it is undergoing both translatory kinetic energy and what? Rotational kinetic energy. So in that essence, we are going to have translatory kinetic energy plus rotational kinetic energy. Meaning that rotational is what? 1/3 mv squared over what? What's translatory? 1/2 mv squared plus what? Rotational 1/3 mv squared. So when we add it up, we are going to have 1/3 mv squared over this plus this will give us 5/6 mv squared. So you can cancel this. Now you have 1/3 times 6/5, giving us this cancel 2, giving us 2/5. And that's the solution. And that belongs to option what? B. Good. Next, find 5 particles of mass 2 kg each are attached to the rim of a circular disc of radius 0.1 meters and negligible mass. Moment of inertia of the system about the axis adding to the center of the disc and perpendicular to its place is dash. Now this question you have to understand. You have to understand that the moment of inertia of the circular disc is not actually what was asked in this question. Reason is that the mass is negligible. The mass is so small that we can approximate it to 0. Rather, what we are talking about is the masses of the body attached to this circular disc. And we've known before now, generally, that the moment of inertia of a body is mr squared. Now, what are the total number of masses attached? 5. So in that case, we are going to have 5 times, the masses are what? 2 kg each, 2 times, while the radius is what? 0.1, then squared. So when we multiply this, we are going to have 10 times 0.1 all squared. So 0.1 all squared is going to give us 0.01. Multiply it by 10, you are getting your what? 0.1 back. So we are going to have 0.1 kilogram meter squared. Kilogram meter squared because that is the unit of moment of inertia. Now, let's look at the next question. The next question says, a stone is wired at the end of a rope 30 centimeters long, makes 5 rads per second. Find the linear speed. Now, one of the confusing things in this question is they gave you a length and you are asked to get the linear speed. And of course, you've known before now that linear speed V is the same as tangential speed. And linear speed is equals to omega r. Now, radius was not given, but let's reason. Let's say that this is u Okay? You have a rope. A mast is tied at the end and you are spinning it. When you are spinning it, it is going to be going round. Is that not true? It's going to go round. When you take your calculations, you are going to find out that the rope that you are spinning is the radius. The length of the rope is going to be the radius. So in this case, V will become omega L. And what was given to us? We are given in revolutions per second. We are given in revolutions per second. Okay? So let's convert that. We are given 5 revolutions per second. So omega is equals to 5 rev per seconds. So converting, one thing you should know is that 1 revolution is equals to 2 pi rads, which is equals to 360 in degrees, which is equals to 1 lap, which is equals to 1 cycle. So let's convert it to 1 revolution. You see, I'm giving the opposite direction so I can be able to cancel them. Is equals to what? 2 pi in radians now. Okay? It's already in seconds. If it's in minutes, we could have converted also. So 5 times 2 pi is giving us what? 10 pi. So that becomes 10 pi what? Meters or 10 meters per second. So using V to be equals to omega L, we now have 10 pi times what is the length? The length is given to be 30 centimeters. 30, you convert it to what? Meters. So that becomes 10 pi times 30 over 100, which is what I showed, is giving us 0.3. And that will give us 3 pi, okay, in meters per what? Seconds. And when you look at the option, that is what? Option C. That is option C. The next question, we are asked to determine the radius of gyration if a uniform rod of mass 35 kg and length 5 meters about an axis through one end and perpendicular to the rod. So let's look at the question. I think I can clean this question down. So going down, we are asked to determine the radius of what? Gyration. Of what? A uniform rod. One thing you should remember is that the moment of inertia of a uniform rod, if it passes through the center, is what? 1 over 12 ml squared. But when it passes from the edges, provided a non-mentioned center, is going to be ml squared over 3. So that should now be ml squared over what? 3. And also, moment of inertia generally is mk squared. So if I call this equation A, call this equation B, I can equate A to B. A to B will now give me ml squared over 3 to be equals to mk squared. So generally we can cancel and do what? Cancel. And our k squared becomes L squared over what? 3. Right? And the radius of gyration k becomes the square root of L squared over what? 3. Therefore, k becomes the square root of L squared is giving us what? L over root 3. Okay? So when you punch that, the length that was given to us is, the length was given to be 5 meters. So you take that 5 over root 3. When you punch your calculator, that will be giving us, when we punch the calculator, 5 by root 3, that gives us 2.886. That is 2.89. Okay, next, and the final question here, we are asked to find the kinetic energy of a thin-walled hollow sphere of mass m rotating with a constant speed v if it has a radius r. Okay, so this question is simply asking us to get the kinetic energy. Now, they never said determine the rotational kinetic energy. Rather, they're asking you to determine the kinetic energy. And remember, in dynamic motion, there are 2 types of kinetic energy: the rotational kinetic energy and the translatory kinetic energy. And that is what you've been asked to determine. Okay? So in that case, the kinetic energy here present is equal to the translatory kinetic energy plus the rotational kinetic energy. But also note, if you are asked a question, if you are asked to determine the kinetic energy of this very body or whatever body along its axis of rotation, if it is spinning at a particular point, it is fixed at a particular point, the only kinetic energy that will be present will be the rotational kinetic energy. Please take note. But in this case, everything is present since it is not rotating or spinning at a fixed point. So going down, translational, remember the moment of inertia for a hollow sphere is 2/3 mr squared, right? Good. And the translational kinetic energy is 1/2 mv squared plus the rotational kinetic energy is 1/2 I omega squared, right? So moving with that, we have 1/2 mv squared plus 1/2. What is the moment of inertia of the sphere? 2/3 mr squared times omega squared. Coming down, we have 1/2 mv squared plus 1/2. This can multiply each other, divide it, we have 1/3 m omega squared r squared. Can you still remember that v is equals to omega r? Therefore, omega squared r squared will give us v squared. I hope you remember. So going down, we have 1/2 mv squared plus 1/3 m. This will now be v squared. So you know how to add fractions. Half plus 1/3 is going to give us 5/6 mv squared. That's the answer. And that happens to be option A. Thank you. Okay, so please, I invite you all to our physical class at Kinematics Tutorials Ekosodi. Okay, it is located at University of Benin Ekosodi Backgate. All right, so I welcome you all, and my prayer is that you are going to have the best of results. Thank you.